Audio test, 1 2 1 2 1 2. Audio 1 2 1 2 3 4 5 4 3 2 1. Audio 1 2 1 2 1 2 1 2. Today we look at the power amplifier of the do-it-yourself transceiver. We did already look at the antenna amplifier, we did look at the bandpass filters, we took a look at the RF mixers, the first mixer, the crystal filter, the second mixer. And we did take a look at the preamplifier, and today we look at the power amplifier. This is the circuit of a power amplifier by Jim WA2EUJ. He won with this design the NXP Design Challenge 2019. He designed a power amplifier with an MRF101 from NXP. It's a $25 a piece LDMOS transistor. He has designed 2 watt in, 100 watt out, and a broad, very broad frequency range from 1.8 to 54 megahertz. So the RF is coming in from here from the left. You have a matching circuit to match the input impedance, and then you have a matching circuit to match the output impedance to go out here with, to be able to go out here with 50 ohms. And then also he has designed a way to apply the bias voltage for a bias current, for the quiescent current here. You apply about, what is it, about 2-3 volts. And the trick is also to thermally couple this diode close to this LDMOS transistor. So when the LDMOS is getting hot, the quiescent current increases, but also this small signal diode is getting hot, and the small signal diode, silicon diode, has -2 millivolts per centigrade and in the forward voltage. So the forward voltage drops, so that the voltage drops here at the gate, and a voltage that drops at the gate reduces then again the current, so you have a compensation of your quiescent current drifting away because of temperature. And then he also has a circuit here, so you can totally shut off the transistor when you're not transmitting. That saves power and heat. So I've modified my design a little bit from Jim's design. I have a different matching circuit here at the input, and I have less feedback here because I'm not using the whole frequency range as Jim was designing his amplifier for. His amplifier is really broadband, and mine is only tuned for 3 megahertz all the way up to maybe 14-15 megahertz. So that's 80 meter to 20 meter. And then I was struggling quite a bit with finding a model for the MRF101. Well, frankly, I didn't find any to use in LT Spice or any Spice model. And what I found is are S parameters. And I converted the S parameters to a subcircuit and added a subcircuit here. And I could do some of the simulations with this, but not the others. And then I was playing around with also using another model I found on the internet. It's a VDMOS, and VDMOS is supported by LT Spice. And I was using this VDMOS, even though this RD100 is not specified all the way up to 50 volt, but yeah, I could do some simulation, but it's not satisfying, of course. But it gave me an idea how the circuit works, and I can explain a few things here. So these are the S parameters I got from NXP. These S parameters are defined only from 30 megahertz upwards. So that was a little bit disappointing. I didn't have any S parameters available. I don't have any S parameters available for the frequency range I'm operating in. What I did is I just copied this line here and defined it for 1 megahertz. So I have between 1 and 30 megahertz the same parameters, which is wrong, totally wrong. But as a first guess, that's what I did. And then you find on the groups IO the mailing list for LTSpice. You can find there a converter, a software, command line software that converts these touchstone S parameter files into a sub-circuit SPICE model library. And I was using this, and that's what you get here. This is then the sub-circuit, and with this sub-circuit you can go ahead and build your own device for LTSpice simulation. And the AC simulation worked well, but the transient simulation didn't work at all. Maybe one short word about this LDMOS. LDMOS, this lateral diffused metal oxide semiconductor, is a MOSFET. And these MOSFETs are very, very popular in RF power amps, 2G, 5G, mobile networks and other stuff. High power, good linearity, high efficiency. And they go all the way up to 3.5 gigahertz. And typically they have a breakdown, the drain source breakdown, more than 60 volts. That means you can work with 50 volts easily, and that gives you these higher voltages give you a lower current for the same power, and low current means less RFI, and so that's why we all like them. And alternatively, you could also use gallium nitride power amplifiers. They have a little higher efficiency, go even a little bit higher up in frequency, and you see them at very high radar applications and so on. So these are the two technologies available today for power RF. And so I don't have any S parameters in my frequency range. So, but in the specification or in the data sheet, you had a few reference circuits and reference designs, and one of the reference designs was specified at 13.56 megahertz, so that's almost a 20 meter band. And you have two numbers here. You have a Z source, an impedance for the source and an impedance for the load. And what he's expecting here, that's my understanding, he's expecting, the LDMOS is expecting 20 plus J10 ohm from the source. That means that the input impedance of this amplifier is the conjugate complex number of the source impedance, so it's 25 minus J10. And the output network, this impedance here is roughly 12.5 ohm, so that's 50 divided by 4. That's what he's probably expecting here on this side of the matching network. So what I'm using typically is this matching network designer from MATLAB. That's an application, an app that you can additionally get for your MATLAB. It's a handy tool. You define your input impedance. That's I think I come with 50 ohms from here from my preamp. I don't really know exactly. I should measure that once. And of course, this is what is specified here in the manual, in the data sheet. So these are the 25 minus 10i ohms that the LDMOS would like to see. You have the choice of different topologies, pi, T, and a simple L topology. That's what I did choose, a simple C and an L. And for the frequency I'm using it, I got this about 1 microhenry and 1.5 nanofarads as C and the L. And you see it's more or less flat here. That's S21, and it drops off at the lower frequencies. These impedances are specified at 13 megahertz. How much is it really at 3 megahertz? We don't know. And there are so many parameters that vary. Temperature has an effect, maybe at higher powers. I've heard Jim was mentioning this once. At the higher powers you have different S parameters, so you really have to do tests on the bench to make sure that your system is stable and linear and fulfills your design criteria. Okay, then after the input we also have to match the output, and the guys who designed this LDMOS, this MRF101, they did a good job because they were designing to output impedance of about 12.5 ohms, and 12.5 ohm is very simple to achieve with a 4-to-1 broadband transformer. These are the same. This transformer here, or this configuration here, and this configuration here is exactly the same. And you have a low impedance side, you have a high impedance side. So the high impedance is 50 ohm, that's the antenna, and you have 12.5 ohm towards the LDMOS. Okay, so that was pretty straightforward. And also a few words to this negative feedback circuit. We have a negative feedback with this capacitor and this resistor. The capacitor just blocks the DC voltage, and we only want to have an AC coupled feedback. And this negative feedback means that you lose gain in the end, but you get a broader bandwidth of your amplifier. And since I'm only using my amplifier all the way up to maybe 14 megahertz, I was reducing the feedback compared to Jim's solution, and I'm also only providing maybe 1 watt typical at the input. And so I was playing around and trying to improve amplification and not lose stability. It also helps for stability reasons. That's important too, by the way. All right. So this is a simulation in the time domain with an RD100 LDMOS. And what you see here on the green line is the input. It is biased. The VGS is around 2.66 volts. That gives us a quiescent current of 100 milliamp, and on top of this 2.66 volts you have your input signal. The blue line is across the load resistor, the 50 ohm dummy load, and the red line is then the instantaneous power load resistor. And when you look at the blue line, the voltage across the load resistor, then you see that whenever the input voltage is positive, you have a nice sinusoidal behavior of your output. But when the input voltage gets negative, then it starts to clamp. And well, that's expected because your total VGS is then getting too low in the nonlinear range, and then it clamps. So that means that your output of this amplifier is more like a type, what is it, B or C even, a type of amplifier. That means you have a lot of distortion and harmonics in your output. But you could get rid of that, and on the bench we try to do this and demonstrate this. You could increase, of course, the VGS, the gate voltage, but that would also massively increase your quiescent current. And the quiescent current of 1 amp instead of 0.1 amp would be 50 watt power dissipation and the DC power. And we are not interested actually in DC power, we are only interested in AC power. And this DC power you have to get rid of that somehow, and you have to make sure you don't damage your MRF101. So now this is not a possible point of operation, that's more theoretical, and that's why we always use these amplifiers as a type B or even C kind of amplifier. Maybe a push-pull configuration would help here, and we would have to try out. So that's for that. And then this is a simulation in the frequency domain. The frequency response of the amplifier, of course, done with this with the S parameters of 30 megahertz, and measuring all the way down, or simulating all the way down to 3 megahertz. So I don't trust this, but it gives you an idea about where the gain could be. It should be roughly about the 30 dB, and we will see on the bench that at least this was plus or minus correct. So we measure the frequency response of the amplifier. We power the preamp we start with 2 megahertz and 500 millivolt peak input voltage. That's on a 50 ohm load impedance or source impedance. And then we measure the output on the scope. And so let's start. This is 2 megahertz. We have a yellow trace, which is the input, and the purple trace is the output of the amplifier into a 50 ohm dummy load. And we have 10 volts peak, 10 volts peak here on the purple output trace. This is 2 megahertz. We go up to 3 megahertz. We have now about a 3 watt output power, and this is now 4 megahertz, 5, 6, 7 megahertz. This is now 5 watt output. And we continue all the way up 8, 9, 10, 11, 12, 13, 14 megahertz, 15 megahertz. That's the 20 meter band. And the amplifier is running on a quiescent current of 0.1 amp, 100 milliamp. And the SIGGEN, however, is not providing exactly constant output voltage over this frequency range, so we have to take a Bode plot, which is doing the relation between V out to V in, and this ratio of V out to V in is then the correct way to measure frequency response. But you got an idea here by just sweeping through the frequencies how this amplifier is performing. We see on this amplifier a perfect sinusoidal wave whenever the gate voltage is positive, and we get a negative or a distorted output when the gate voltage is going to be negative. We get into a nonlinear range. We could change this, of course, by increasing the quiescent current. Let me do this here quickly. I change the quiescent current to significantly higher currents, like here maybe an amp or so. For a short period of time you can do this. Of course the MRF101 is getting really, really hot, and this is not a good operation point. And so what we have here is something like a B or maybe even C amplifier, something like that. And this distortion with this output signal, you are not allowed to go on the air at all. You always have to have a bandpass filter like we have here in our circuit. This is the bandpass for the 3 different bands. This is how you configure the Bode plot on the signal scope. You define the frequency range, you define the kind of a sweep, that's a single sweep, a linear sweep. I want to measure 100 points. I do have an output voltage of 0.5 volt. And this information about frequency, output voltage, and also the load impedance is going to be sent over to the SIGGEN through this USB connection. I can test quickly the connection. It's perfectly connected. And according to this setup, the frequency generator is generating exactly what the scope is asking for. And so we can let it run now. Change to operation, and it starts to measure now the Bode plot. It adjusts the frequency. We are now at around 300 kilohertz, and it goes all the way up. And you can see how this measurement is going to be done. We are now at 3.4 megahertz. This is 7 megahertz. And you see here almost 40 dB amplification. It's actually here, it's 39.6 dB at this marker. At this point over here we have 34 dB, and at this marker over here we have 39 dB. So we have a 5 dB increase from what is this, 3.5 megahertz, 3.7 megahertz to 11 megahertz. It's about plus 5.6. So well, it's pretty much okay. It's increasing a little bit on the higher frequencies, but I can of course live with that. So this is the output of the amplifier after the low pass filter at 7.1 megahertz, 0.5 volt peak-to-peak input voltage at the preamp. And you see that the output pretty much looks like a sinusoidal signal now. And with this, you think you should go and should be able to go on air. But if we look at the spectrum, so at the quiescent current of 100 milliamp, we have a difference between the first and the second harmonic of about minus 32 dB. You could increase this difference by increasing the quiescent current, as we saw before, that we drive the amplifier more towards a class A amplifier. Let me try to do this. I increase now the quiescent current to, let's say, almost an amp. And what we should get now, yes, we have almost 39 dB down. It could be 40 dB down with even more current. But of course, this is not a valid point of operation. So let's move down to 100 milliamp quickly before we burn up the whole thing here.